10th ICSE Physics Chapter 7 Part A Reflection of Sound Waves and Echoes. Sound waves sounds easy. In ninth standard we had studied that sound is produced when a body vibrates and sound requires a material medium for its propagation. The audible range of frequency of sound is 20 Hz to 20,000 Hz. Our ears are sensitive only to this limited range. Of course, the actual values depends from person to person. You can test it by listening to sounds in this range on some YouTube video. Now, sound whose frequency is less than 20 Hz is called infrasonic, and if the frequency is more than 20,000 Hz, it's called ultrasonic. For example, 50,000 Hz sound is ultrasonic, we can't hear it. There is a joke about sound with 50,000 Hz frequency, but you may never have heard about it. Now, the speed of sound depends on two factors: elasticity and density of the medium. Notice that speed of sound is inversely proportional to the square root of density. But then by that logic, gases, which have the least density compared with solids and liquids, should have the highest velocity. But on the contrary, speed of sound is highest in solids. Like in steel, it is around 5,100 meters per second, compared to a measly 340 meters per second in air. Well, that's because of elasticity. The elasticity in solids is far greater than in liquids and gases. So overall, speed of sound is maximum in solids and least in gases. Now there are a few definitions. First of all, amplitude. It's the maximum displacement of the particle of the medium on either side of its mean position. It's easy to understand amplitude if we can plot a graph for a sound wave. Now this is a transverse wave. Sound is not a transverse wave. Sound is a longitudinal wave, something like this. But a transverse wave is easier to study. So as you can see, the amplitude is the height of the wave. Now imagine that a transverse wave has been set up in a rope. The particles of the rope are oscillating up and down, that is perpendicular to the direction of the wave. The maximum displacement on either side is called the amplitude. A transverse wave has a crest and a trough, whereas a longitudinal wave has regions of high pressure and density called compressions and low density and pressure called rarefaction. Sound travels through solids, liquids and gases in the form of a longitudinal wave. Very rarely does sound travel through solids in the form of a transverse wave. Longitudinal waves can be understood with the help of a spring. If a wave is set up on one end, then the energy is transferred to the next layers. There are compressions and rarefactions alternately. But here the particles of the medium are oscillating horizontally, that is, in the direction of the wave. And notice that the particles themselves never move till the end. Be it transverse or longitudinal, the particles simply oscillate about their mean position because the medium has elasticity. The energy is being transferred, and sound is a form of energy. Sound is a mechanical wave because there is always a conversion between kinetic energy and potential energy and vice versa. It's like the pendulum of a clock. Now the wavelength here can be understood to be the distance between two consecutive crests or two consecutive troughs, or the distance traveled by the wave in one time period is called the wavelength. Time period means the time taken by a wave to complete one oscillation, one vibration. And frequency will be the number of waves per second, number of oscillations per second. Time period SI unit is seconds. Wavelength and amplitude have SI unit meter. Lambda is a symbol of wavelength. Back to the 10th standard book, wave velocity is the distance traveled by the wave in 1 second. And the formula for that is F into lambda, that's frequency into wavelength. Frequency is the reciprocal of time period. So if a second's pendulum has time period of 2 seconds, then the frequency of that pendulum is 0.5 Hz, 1 upon 2. That is infrasonic sound, and that is the reason why we can't hear the oscillation of a second's pendulum. Now remember that the frequency of a wave depends on the source, the vibrating source. It does not change even if the wave travels from one medium to another medium. The velocity can change, the wavelength will change, the intensity will change, but the frequency never changes. Sound is a mechanical wave, also called elastic or longitudinal wave. So sound cannot travel through a vacuum. So if there's an explosion in space or on the moon where there is vacuum, the sound cannot be heard. Astronauts communicate with each other in space with the help of electromagnetic waves, radio waves, similar to the waves we use for our telecommunication. Electromagnetic waves are transverse and they don't require a material medium. They can travel even through vacuum. Electromagnetic waves are not mechanical waves, they don't require a material medium. So, what is oscillating then? It's the electromagnetic field which oscillates perpendicular to the direction of the wave. In fact, the electric and magnetic field are perpendicular to each other. More about these in chapter 6. Electromagnetic field permeates all of space and time. Light is just a tiny fraction of the electromagnetic waves. Our retinas have evolved to see just a part of these electromagnetic waves. There's nothing special about light. The Vibgyor colors are just a range of frequencies we can see. If the frequency is more than 4000 angstroms, we call it ultraviolet. And if the frequency is less than that of red, that is less than 8000 angstroms, we call it infrared, which is also known as heat. Some animals like snakes can see heat. Even a night detection cameras, heat detection, they detect the infrared coming out of warm-blooded animals or from some machines. Microwaves, radio waves have large wavelengths. Gamma rays have the smallest wavelength. Then we have X-rays. More about this in chapter 6. But one thing is very common to all of them. All of them travel at the speed of 3 into 10 raised to 8 meters per second in vacuum or in air. All of them obey the laws of reflection, refraction, diffraction, etc. Just like light does. It's just that we can see only light. Some insects like bees can even see ultraviolet. That is where they are attracted towards the violet bulbs. So the difference between sound and light. Well, light are electromagnetic waves, they are mechanical waves. They can travel in vacuum, they can't. Speed is very high compared to sound, which has some consequences. For example, we first see lightning and then hear the thunder. And these are all transverse waves, whereas these are longitudinal waves, especially in fluids. In solids, they may be longitudinal and rarely transverse. Definitions have to be marked for longitudinal and transverse waves. And remember, transverse waves can travel only through solids and the surface of liquids because they can be formed only if the media possess rigidity, which is not possible inside liquids or inside gases. Now, there's a special formula to calculate the velocity of longitudinal waves like sound, which is velocity is equal to square root of gamma, pressure upon density. Gamma is a constant, and pressure is a factor which surprisingly does not affect velocity because if pressure of gas decreases, the density also decreases, so the ratio remains same. So density of the medium is more important. There are various other factors which affect velocity of sound. For example, temperature. As temperature of a gas increases, the volume increases and the density decreases. And if density decreases, the velocity also increases. Also, as humidity of air increases, velocity of sound increases because humid air, surprisingly, is less dense compared to dry air. Yes, moisture has less density than air. That is why clouds float in the troposphere. And 1 degree Celsius rise in temperature increases the speed by roughly 0.61 meters per second. Now for transverse wave, there is a special formula. The velocity is equal to square root of the tension in the string upon mass per unit length of the string. That's all you need to know. Now remember that these waves undergo refraction when they are traveling from one medium to another. Just like light does, even sound can refract. But not when the sound wave is perpendicular to the boundary separating the two media, because in that case the angle of incidence is 0. So the angle of refraction will also be 0. Something like this. Speed will change, wavelength will change, direction hasn't changed because it was normal. Otherwise, refraction happens not only in light, but also in sound. Notice how the direction changed. More about it in chapter 4. Remember, the smallest quanta of an electromagnetic wave is a photon. So they are like particles. Next topic is reflection of a sound wave. Well, just like light, even sound obeys the two laws of reflection. The angle of incidence is equal to the angle of reflection, and the incident ray, reflected ray, and the normal at the point of incidence all lie in one plane. Mark the definition of reflection of sound. So notice that the incident ray, reflected ray, and the normal all lie in this plane of the paper. It doesn't come out of the paper. This is true not only for light, but even for sound. Now, reflection of sound does not require a smooth and shining surface like a mirror. It can be reflected by any kind of medium. The only requirement is that the surface should be bigger. The surface should be bigger than the wavelength of the sound. And this phenomenon of reflection is used in devices like the megaphone or the speaking tube, which is often used by directors while giving instructions while shooting. It's shaped like a cone, like this. And here's the input of sound so that the sound can travel farther and can be louder in one direction. Sound boards are concave in shape so that they can focus the sound onto a single point. Ear trumpet is a hearing aid. It also uses the phenomenon of reflection of sound. Now mark the definition of an echo. The sound heard after reflection from a distant obstacle, after the original sound has ceased, has stopped, is called an echo. So even now, sound is getting reflected from the walls surrounding me, but I don't hear any echo because of persistence of hearing. You see, there should be a time gap of at least 0.1 second between the original sound and the reflected sound for me to be able to distinguish between them. Only then can I hear an echo. So if we calculate using the formula distance is equal to velocity into time upon 2, you see velocity is total distance, that is to and fro both, upon time. If you cross multiply, you get this. Now, velocity in air normally is 340 meters per second and time interval is 0.1 second. That means the reflecting surface should be at least 17 meters away for me to be able to hear an echo. In fact, if we are in water, then the speed of sound is more. It's like 1500 meters per second. So in water, for an echo to be heard, the reflecting surface should be at least 75 meters away. Mark this as a give reason. And remember this phenomenon of being able to hear an echo only after 0.1 second is because of persistence of hearing. Now sometimes there are repeated reflections at reflecting surface and the sound gets prolonged because of multiple echoes, multiple reflections. You say a word once and that word is heard multiple times overlapping. This effect is called reverberation, which happens in monuments like the Taj Mahal, Sikandara, etc. Now there are 3 conditions for an echo to be heard. One is the minimum distance requirement. Second is that the size of the reflector must be large enough. And also the intensity of sound should be great. If you say a name very feebly at the echo point, then you may not be able to hear the echo. It should be loud enough so that it's audible. Now how to determine the speed of sound by the method of echo? Well, imagine you are at an echo point with some reflecting cliff far away, say 50 meters away at least. So you make a sound and you start the stopwatch. And when you hear the echo, you stop the stopwatch. You know the distance between the 2 points, maybe because of Google Maps. You know the time. So using this formula, you can find the velocity of sound. Do this experiment several times to get a more accurate average value because there are many factors which influence this. The human reflex error, wind direction. Now there are many uses of echoes. 2 major uses are sound ranging and echo depth sounding. For both, we use ultrasound because it has 3 unique properties. First of all, directivity. It travels undeviated through a long distance like laser for light. Similarly, it can be confined into a very narrow beam, just like laser. And it has high energy, so it travels a long distance. It is not easily absorbed in a medium, so it can travel a long distance. Remember, ultrasound means sound with frequency more than 20,000 hertz. It doesn't mean it is louder than the usual normal sound. There is no link between loudness and frequency. It's just that it's highly pitched and we can't hear it. Even the speed of sound is same whether it is sonic or ultrasonic. Animals have different audible ranges. Bats can hear ultrasonic sound up to 100,000 hertz frequency. In fact, they use sound ranging to detect an obstacle in their path. So mark this definition of sound ranging. They use a reflection of sound. They produce ultrasound. A tree or a prey reflects this. They hear it. They quickly use the formula V is equal to 2D upon T and calculate the location of that obstacle, and they can change their direction accordingly. Dolphins also can detect their enemy by emitting ultrasonic waves and hearing the echo. They use it for hunting and their prey. So we were inspired by these, and we have developed technology and machines which uses the same phenomenon. Fishermen can use ultrasound to locate a school of fish or a shoal of fish. Sonar stands for sound navigation and ranging. In this technology, the bottom of the ship has a transmitter which transmits ultrasound. An obstacle like the ocean bed or a submarine will reflect it, and the receiver will receive it. All the data is fed into a computer which quickly calculates the depth of the ocean or that enemy submarine. Now, this process is called echo depth sounding. Note that echo depth sounding is a specific application of sound ranging. Sound ranging is used by fishermen to calculate the distance of fish. But when you use it specifically to find the depth of sea, it is called echo depth sounding. Radar is very similar, radio detection and ranging, but it uses radio waves, not sonar, not sound. Because when it comes to aeroplanes and fighter planes, sound is too slow. There are missiles headed towards the plane which are faster than sound. So instead of noticing the beep beep on your sonar screen, the missile will hit you and you'll become a blip. But radar, well, radio waves have a velocity of 3 into 10 raised to 8 meters per second, which is very fast. It'll be able to detect enemy ships, fighter planes faster. In water, we use sonar. Echoes are also used in the medical field. In ultrasonography, the ultrasound is emitted by a machine. It can pass through soft tissues. They are reflected by the hard tissues, captured by the same machine. The computer uses all this information to create a black and white image of the fetus in the womb, or it can be used to study any of the other organs of the body. Echocardiography is used to obtain the image of a human heart. One more use is that it is used by geologists to detect the presence of minerals in the Earth's crust.
Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.